Good morning to all of you. This is Rama Krishna from Yale University delivering the series of lectures on heat transfer. Today's topic is heat transfer through a slab with internal heat generation. This topic belongs to one-dimensional steady-state heat conduction with internal heat generation. So far we have seen the one-dimensional conduction problems without internal heat generation. Now we will move ahead. What happens if there is an internal heat generation? And how to consider the temperature variation and how to account for the heat transfer in that slab by means of conduction. So at the end of this session, you will be able to understand what are the different sources of internal heat generation and what is the governing equation for conduction with one-dimensional steady-state internal heat generation, and how to solve it, and how to apply boundary conditions to solve that problem, and what is the shape of temperature profile in such slabs with internal heat generation, and how to obtain the position and the magnitude of maximum temperature within the body when there is internal heat generation. Now coming to the different sources of heat generation. In the derivation of three-dimensional conduction heat equation through a slab, we have assumed that there is some internal heat generation within the elemental volume, Q dot, watt per meter cube. Where from this internal heat generation will arise, and what are those sources? First one is electrical current passing through the resistor. Through the resistor. So if the material is in resistance, when current is made to pass through that, it resists the heat current and thereby it generates some amount of heat given by the formula Q equal to I square R. It could be one source, particularly in boiler plates, electrical boiler plates, in electrical wires. When current is made to pass through, they generate some amount of heat energy. It is an internal heat generation phenomenon. And nuclear reaction in a fuel element is also another source of heat generation due to mass disintegration. And in case of chemical beds, exothermic chemical reaction may occur, and thereby it also generates some amount of heat. Absorption of radiation such as solar energy or gamma rays will also lead to generation of heat internally. So these are the sources of heat generation within the solid element, and hence in such conditions how to consider the heat transfer problem and how to determine the variation of temperature within the slab, we will take it now. And please note that heat generation is a volumetric phenomena. That means throughout the volume it generates uniformly, and that is why we use, whenever there is a heat generation, we use the symbol Q dot, watt per meter cube. Per unit volume, what is the amount of heat generated? Before going to the problems on internal heat generation, now let us see how to apply the boundary conditions for a plain wall or slab while solving a conduction heat transfer problem without internal heat generation. Once you understand this, adding one more term will give you the solution for with internal heat generation. So take a slab, one phase is maintained at T1, other phase is maintained at T2. The entire line in y direction is at T2. That means there is no variation in y direction. So the temperature at this point, please note the arrow which I am moving. The temperature at this point is T2. Here is also T2. Here is also T2. Here it is also considered as T2. Here also as T2. So there is no variation in temperature along y direction. So the heat transfer in y direction is neglected. Similarly, the temperature here is T2. The temperature here is also T2. The temperature here is also T2. Here is also T2. At the end is also T2. So in Z direction also, I am not considering the variation of temperature. Since there is no gradient, there is no heat transfer in Z direction. Temperature is only varying in X direction from T1 to T2. T1 being greater than T2, heat flows from higher temperature to lower temperature. So this is a one-dimensional conduction problem wherein I am not assuming any internal heat generation, without internal heat generation. So the governing equation to solve this problem is d square T by dx square equal to 0. So I am not considering y direction and I am not considering z direction heat transfer, and there is no internal heat generation, and we assume it is in steady state. So therefore the governing equation becomes d square T by dx square equal to 0. Integrate it once, you will get dt by dx equal to C1. Again integrate it, you will get T equal to C1x plus C2. So this equation consists of two constants, C1 and C2, and it gives the temperature as a function of x. So this is the temperature distribution equation in a slab as a function of x. To determine the constants C1 and C2, at least you have to frame two equations. So to develop the two equations to solve C1 and C2, we will consider the boundary conditions. That means on the boundaries of this object, at some point, if you know the temperatures, then we use that data to solve the problem, to solve this equation which contains two variables two constants C1 and C2. So the first condition what we know is, on this phase I have assumed the temperature T1. So at x equal to 0, T equal to T1 is the first boundary condition. And we know another condition, that is on the other side of this phase the temperature is given as T2. So at x equal to L, the T equal to T2. So by substituting condition 1 in the equation, at x equal to 0, then C1 into 0 becomes 0. T equal to T1, so T1 equal to C2. You will get C2 value as T1. Now substitute the boundary condition 2, that is at x equal to L, T equal to T2. So T equal to T2, C1 at x equal to L, so C1 into L plus T1, which implies C1 is T2 minus T1 by L. In the place of C2, I have already obtained the value as the T1 that I am substituting here. So I got C1 equal T2 minus T1 by L. Hence, you can write the equation for temperature distribution T equal to C1 T2 minus T1 by L into X plus T1. So this is the temperature distribution equation in the slab without internal heat generation. So by using this equation, at any point x, you can determine the temperature T, while x is varying from 0 to L. So along the thickness of the slab, where conduction heat transfer is occurring, at any point x, you can determine the temperature T because we know the values of T1, T2 and L. This is a linear equation, and hence the temperature profile in a slab without internal heat generation is a straight line. We have seen it several times while solving the problems on conduction heat transfer through a slab without internal generation earlier sessions. And now this gives only the temperature distribution equation in the slab, but how to determine the heat transfer? Follow carefully. The heat enters into the element at x equal to 0 and it leaves at the element at x equal to L. So the conduction heat transfer starts at x equal to L and ends at x equal to 0 and ends at x equal to L. So we use that condition. Q equal to, according to Fourier law, minus Ka dt by dx, where this dt by dx conduction you have at x equal to 0. So minus Ka and dt by dx we got here as C1, and the C1 value T2 minus T1 by L. So substitute that, minus Ka C1 minus Ka T2 minus T1 by L, take minus sign inside, Ka T1 minus T2 by L is the conduction heat transfer through a slab in one-dimensional without internal heat generation under steady state condition. Understand? And the governing equation is d square T by dx square equal to 0. Now as seen earlier, if within this slab you have any chemical reaction or electrical current passing through it, thereby it offers resistance and generates heat, or some other heat source is there which is generating, say, q dot watt per meter cube, then what happens? So now let us consider a slab of thickness L having width W and height H. So as you look at this, the volume of this slab is L into W into H. And I am assuming the heat generation in this volume is Q dot watt per meter cube. So this is the heat generated per unit volume, Q dot. So if you want total heat generated within the slab, you will find by multiplying this Q dot with volume. So Q dot into V is Q into L into W into H, whereas this W into H is nothing but the face area of the slab or the area normal to the direction of heat flow. Now if you look at it, the amount of heat is generating, imagine exactly at this center line. Of course it is a volumetric phenomena, but the point of heat generation, say, is at x equal to 0. Now if you move to the left hand side, the boundary becomes at x equal to minus L by 2, and on the right hand side the boundary is distinguished by x equal to plus L by 2. So x varies from minus L by 2 to plus L by 2, so total thickness is L. And heat is generating exactly, imagine at the center, the temperature will be maximum at the center, the point of heat generation. This heat which is generated internally within the slab reaches the walls by means of conduction. And then it enters into the environment by means of convection. And we are assuming that the convective heat transfer coefficient outside is H0 on both sides of the faces, and the surrounding fluid temperature is T alpha. Since the convective heat transfer coefficient is same and the temperature of the surroundings is also same on both sides, the surface temperature should be same, Ts, Ts. Heat is generating at the center, so the temperature will be maximum at the center and minimum at these surfaces. And because both surfaces are exposed to the same kind of environment, the temperature of both faces will be same. So the heat that is generated at the center reaches the walls by means of conduction, and that amount of heat reached the surface by conduction will enter into the environment by means of convection. So according to energy balance, the total heat that is generated within the slab Q dot L into A will enter into the environment from both the faces 2 times. From each face H naught A into Ts minus T alpha. From left face H naught A into Ts minus T alpha, and from right face also it is H naught A into Ts minus T alpha. So the total heat generated within the elemental volume under steady state condition will reach the surface and enter into the environment by means of convection. So this is the fundamental equation as per the law of conservation of energy. So we know Q dot and AA gets cancelled. We know L, we know T alpha, but we don't know the surface temperature. So by using this equation, the surface temperature can be obtained by Q dot L by 2H naught plus T alpha. As I said earlier, the surface temperature on both faces will be same because the both faces are subjected to same convective environment and the same convective heat transfer coefficient, hence they will be same on both sides. Now the governing equation for conduction with internal heat generation is d square T by dx square plus Q dot by K equal to 0. One dimensional steady state conduction heat transfer through a slab with internal heat generation is d square T by dx square plus Q dot by K equal to 0. So that gives d square T by dx square equal to minus Q dot by K. Integrate once, you will get dt by dx is equal to minus Q dot by K into x plus C1. Again integrate, you will get T equal to minus Q dot x square by 2K plus C1x plus C2. This is the temperature distribution equation within the slab. We know that the heat generation point, the temperature will be maximum inside the slab and it will be minimum at the surfaces because both surfaces are exposed to the environment, and this is a quadratic equation representing a parabola. Therefore, the temperature distribution within a slab with internal heat generation is parabolic in nature, like this. Now you have two constants, C1 and C2, as we have seen earlier. A second order differential equation requires two boundary conditions to solve the problem. So here also you got two constants, C1 and C2. To solve this equation, you have to apply boundary conditions for the given problem. First boundary condition is, we have already found Ts. So at x equal to minus L by 2, T equal to Ts, one boundary condition. Other boundary condition, we know even at the other phase also temperature is Ts. So at x equal to minus L by 2 as well as at x equal to plus L by 2, T equal to Ts. You understand? So either at L by 2 or at minus L by 2, the temperature is Ts. Two conditions. If you substitute these two conditions, you will get the solution. There is one other important point which you have to remember. Because we are assuming that heat is generating at the center, both surfaces are at same temperature, because the environment is also at same temperature. Another important point is the maximum temperature occurs at the center. So which indicates that the gradient dt by dx, or if you draw a tangent to this curve, the slope of that will be equal to 0. So T equal to T maximum, the temperature reaches maximum at x equal to 0, center line, and hence dt by dx equal to 0. This is also a boundary condition which you can use to solve the problem. Any two conditions are enough to solve this temperature distribution equation having two constants C1 and C2. Depending on our convenience, we choose any two conditions. These first two conditions we have seen are first kind of boundary conditions because they are directly giving you the value of T at a position x. Whereas this boundary condition is not giving you the value of T directly, but giving a conditional statement dt by dx equal to 0, from which you have to determine the value of T. Hence, this type of condition is called second kind of boundary condition. First kind of boundary condition and second kind of boundary condition. Okay. So by applying these boundary conditions, we get first boundary condition, that is dt by dx equal to minus q dot x by k plus C1. So if you put x equal to 0 in this, dt by dx is 0, so therefore C1 equal to 0. And by applying the second boundary condition at x equal to L by 2, we get Ts, T equal to Ts minus q dot L by 2 whole square, L square by 4k plus C2. So C2 equal to Ts plus q dot L square by 4k. Hence, by substituting the values of C1 and C2, you get T minus Ts is equal to q dot x square by 2k plus q dot L square by 4k. Suppose one of the surface is insulated like this. Heat cannot move from the left face. The heat generated within the slab has to come out only from right hand side face. And the heat that is going by means of conduction towards the left face cannot enter into the environment, and hence it starts accumulating there, thereby the temperature goes on increases. The temperature increases at the left face and reaches maximum, then it develops a gradient in the positive x direction, and from this point onwards also it starts conducting heat only towards the right phase. So now the maximum temperature occurs at the insulated phase rather than at the point of heat generation. And another important point is, when one of the phase is insulated like this, the total heat generated will leave from only one phase. So the equation is Q dot LA, L is thickness, A is the phase area, volume, is H naught A into Ts minus T alpha. So that gives you Ts equal to Q dot L by H naught plus T alpha. And again, by applying the general conduction heat equation with internal heat generation, you will get T equal to minus Q dot x square by 2k plus C1x plus C2. So use the first boundary condition at XL, at x equal to L, T equal to Ts, and at x equal to 0, T equal to T maximum, that is dt by dx equal to 0. So if you use this condition, you will get C1 equal to 0, and by applying the second boundary condition, that is at x equal to L equal to T equal to Ts, you will get C2 equal to Ts plus Q dot L square by 2k, and hence the temperature distribution equation becomes T minus Ts equal to minus Q dot x square by 2k plus Q dot L square by 2k. So temperature distribution equation can be found by using the fundamental governing equation for conduction with internal heat generation under steady state and one-dimensional, and solving that, and thereby applying the boundary conditions, etc. So first to take the equation and integrate it to get the temperature distribution, and then identify the boundary conditions, substitute the boundary conditions to solve C1 and C2. And to get those boundary conditions, you may have to use the total amount of heat generated as a source to determine the surface temperatures, etc. And because the equation contains heat generated per unit volume, convert it into total heat generation, capital Q, by multiplying with the volume. So one of two sample problems we will see how to tackle these cases with internal heat generation. Consider a plane wall of 10 centimeter thick as shown here, generates heat internally at the rate of 4 into 10 power 4 watt per meter cube when an electric current is passed through its center. If H is equal to 2 per meter square Kelvin, determine the surface temperature, maximum temperature in the wall, and assume the thermal conductivity of the slab is 15 watts per meter Kelvin and the temperature of the surroundings is 20 degrees. Governing equation for this type of internal heat generation problem under one-dimensional steady state condition is d square T by dx square plus Q dot by K equal to 0. The solution of this in terms of temperature distribution equation as a function of x, by integrating it twice you will get T equal to minus Q dot x square by 2k plus C1x plus C2. Now the internal heat generation is given as 4 into 10 power 4 watt per meter cube, which will be converted into total heat generation by multiplying with the volume of it, let us say length L and face area A, and that heat generated at the center reaches the walls by means of conduction and enter into the environment from both the faces by means of convection. So it is equal to both the faces. So 2 into H convective transfer coefficient A surface area into Ts minus T alpha. So therefore Ts equal to Q dot into L by 2H plus T alpha. By substituting the values you will get 60 degrees centigrade. And the boundary conditions are, we know dt by dx, that is Q dot x by k plus C1 is 0 at x equal to 0 center, and hence C1 is 0. Now another condition is at x equal to 5 into 10 power minus 2 meters, that is at x equal to 5 centimeters, the temperature is the surface temperature, which we have obtained as 60 degrees centigrade. So applying this condition, 60 equal to minus Q dot x square by 2k plus C1 is 0 plus C2. Q dot 4 into 10 power 4, x square 5 into 10 power minus 2 whole square by 2k, 2 into 15, minus sign is missing here, will give you the value of C2 as 63.33, and thereby you can write the equation T equal to minus Q dot x square by 2k plus 63.33 degrees centigrade. See parabolic equation. So that is why Ts on both sides is same. Heat is generating at the center. The environment condition on both sides is also same. So the maximum temperature in the wall you can obtain by substituting x equal to 0. So put x equal to 0, you will get T maximum equal to 63.33. Is hidden here, 63.33. Let us take one more problem. Considering that the face of the slab given in the last problem is, one face is insulated, you are asked to determine the surface temperature and maximum temperature in the wall. The difference between this and earlier problem is, whatever heat is generated here internally will be able to leave to the environment only from one face, because the other face is insulated. So therefore, the total heat generated Q dot into A into L is equal to HA into Ts minus T alpha. There is no multiplication of 2 because it is leaving only from one face. That will give you Ts equal to 100 degrees centigrade. Q dot L H. H is only, the H, only one H is there. So that will give you the value of Ts as 100 degrees. This is 4 into 10, 40. 10 power 4, 10 power minus 2 is 10 square. So 4000. 4000 by 50, 80. 80 plus 20, 100 degrees. Correct. Now the other boundary condition is, as we have seen earlier, when there is no possibility for heat to travel from the left face into the environment, it starts accumulating here. Therefore, the temperature at this place goes on increases, and it sets up a gradient in positive x direction, so that heat will conduct again from this point to the other side. So the maximum temperature occurs at the insulated surface. So you can use that condition at x equal to 0, T equal to T maximum, that is dt by dx equal to, and at x equal to L, of course, T equal to Ts. So dt by dx is minus q dot x by k plus C1 equal to 0. By substituting x equal to 0, it implies C1 equal to 0. And at x equal to 10 into 10 power minus 2, T equal to 100 degrees. So by substituting 100 equal to q dot x square by 2k, C1 is 0, so C1x term vanishes, plus C2. So hence C2 equal to 113.3. So temperature distribution in the wall is given by T equal to minus q dot x square by 2k plus 113.33. And now if you want maximum temperature, put in this equation x equal to 0, you will get T max is equal to 113.33. That's all. So the most important thing you have to understand here is how to choose the value of x and where to choose. See, if you start the coordination system from this phase at x equal to 0, being T equal to T maximum, dt by dx is 0, and hence you will get C1 equal to 0. Whereas in the last problem, we have taken x equal to 0 at the middle because we are aware the maximum temperature occurs at middle. So at x equal to 0, dt by dx in this problem also becomes 0, leading to C1 equal to 0, and solution becomes simple. But here the boundaries will be x varies from minus 5 to plus 5, whereas in this case the boundary is x varies from 0 to L. So by carefully choosing the initial coordinate system, the 0 point, origin point, you can solve the problem in a simple way. That is the object. Now let us take a different problem. Imagine there is a steel plate of 1.25 centimeter thick. It is represented as 12.5 mm here, and 10 centimeter wide, maybe this W, consider it as W, 10 centimeter wide. The temperature of one surface of the plate is at 80 degrees and that of other is 95 degrees. He has given T1 and T2. Find the temperature distribution across the plate, the value and position of maximum temperature in the plate, and also calculate the total amount of heat generated per meter length and flow of heat from each surface of the plate. So meter length of the plate you have to find. Take resistivity for steel 12 micro ohm centimeters and thermal conductivity of it is 54 watt per meter Kelvin. So when you pass current through the steel material having resistivity, it generates heat energy, and that heat energy generated in the slab will reach the surfaces by means of conduction and enter into the environment by means of convection. The surrounding surface temperatures on both sides is same, and the convective transfer coefficient is also same. Though the surrounding temperature and convective transfer coefficient on the faces of the plate to which it is exposed is same, but the temperatures on one side is higher and one side is lower, indicates that heat is not generated exactly at the center. Because the right surface is at higher temperature than the left surface, perhaps heat is generating slightly nearer to the right face. Thereby, the right face temperature is higher than the left face temperature. So, it indicates that because of different temperatures being maintained at different faces, it reflects that heat is not generating exactly at the center. That is the inference which you have to draw from this problem. Now again, the governing equation is d square t by dx square plus q dot by k equal to 0. And solution of that is t equal to minus q dot x square by 2k plus c1x plus c2. One phase is given maintained at 80, other phase is maintained at 95. So two boundary conditions are known to us. At x equal to 0, t is 80, and other one at x equal to 12.5 mm, t is 95. And what is this q dot? Internal heat generated per unit volume. And to determine this q dot, first you have to determine what is the total heat generated in the slab. Because of the current passing through it, it generates a heat energy Q, which is equal to I square R, and R is the resistance, I is the current flowing through it. The current flowing through the plate is given as 34,000 amps, whereas the resistivity is given, not the resistance. You have to find resistance, R equal to rho L by A. The resistivity, length of the conductor, meter, it is given per meter length, by cross sectional area 12.5, that is it is given as 10 centimeter wide into 1.25 conductor cross sectional area, that is 1.25 into 10 into 10 power minus 4. You will get the resistance in ohms. Current is passing perpendicular to this paper to the center. So this area we have to consider for calculation of resistance. Now Q equal to I square R, 111 kilowatts. Q dot, Q by volume, L into W into T, where L is 1 meter, width is that 10 centimeters, and thickness is 12.5 mm. You will get Q dot. Now boundary conditions: at x equal to 0, t is 80. At x equal to 1.25 in 10 power minus 2 centimeters, t is 95 degrees centigrade. By substituting t equal to 80 at x equal to 0, you will get C2 equal to 80. And other condition, t equal to 95 at x equal to 1.25 in 10 power minus 2 will give you C1 equal to 1147.5. Now the temperature distribution equation is T equal to minus Q x square by 2k plus 1147.5 x plus 80. Now maximum temperature. First order derivative of this should be equal to 0. dt by dx equal to 0. So that means minus q dot x by k plus 1147.5 something 0.5 equal to 0. So that gives x equal to q dot into k by x is equal to 11,475 into k by q dot, which will give you 6.97 millimeters. That is, maximum temperature occurs at 6.97 millimeters from left to face. It is not There is another 5 here. And to determine the maximum temperature, in the temperature distribution equation, let us substitute x value 6.97 into 10 power minus 3. We will get T maximum equal to 120 degrees centigrade. So carefully observe, you got the value x is equal to 6.97 mm. So that means the plate width is 12.5 mm, half of it is 6.25 only. But maximum temperature is obtained at 6.97 mm, so slightly towards right side. That is the reason why the right face is at more temperature than the left face. Now how to determine the heat transfer? The heat flowing at x equal to 0, that is Q at x equal to 0 is minus Ka dt by dx at x equal to 0. That is the heat at x equal to 0 by means of conduction reaching there and entering into the environment by means of convection. So it is minus 54, and the area normal to the direction of heat flow 1 meter into 10 centimeter width into dt by dx. The dt by dx is q dot x by k less 11475.5. You will get minus 61.967 kilowatts. Minus sign indicates it is doing towards left side. Similarly, the conduction heat at the right face, that is at x equal to 1.25 in 10 power minus 2 equal to minus Ka dt by dx at x equal to 1.25 in 10 power minus 2. By substituting the x value here as that, you will get plus 49 kilowatts. This is towards positive x side. So the total heat generated in the slab goes towards left side and also towards right side. The amount of heat that is going towards left side is 61.967 kilowatts, and that going towards right side is 49 kilowatts, and hence the total heat generated within the slab is sum of these two 110.977 kilowatts. That is what we have got in the beginning also, the capital Q 111 kilowatts. So that is what it says, it is satisfied. 110.977 is 111 kilowatts. So this is about the plane wall conduction heat transfer in a plane wall or slab with internal heat generation. So what are the important points we have discussed now in this? Let us see. The points to be remembered are the fundamental, the governing equation for one-dimensional conduction under steady state with internal heat generation is d square T by dx square plus q dot by k equal to 0 for a slab. It means for objects which are described with the help of XYZ coordinate system. And it is given by minus q dot x square by 2k plus t1x plus c2. And since this is a quadratic expression, the temperature profile within the slab with internal heat generation is parabolic in nature. And the maximum temperature occurs at the point of heat generation if it is specifically mentioned. And in case of insulated surface, the maximum temperature always occurs at the insulated surface. To solve this equation, you need two boundary conditions. Maybe those two boundary conditions could be first type conditions, or one first type condition, another one second type condition. Wherever the maximum temperature occurs, the temperature gradient becomes 0, so that we can utilize it as a boundary condition to solve this temperature distribution equation in a easy manner. So I advise you to give a further reading of these books, maybe second chapter I think, with internal heat generation. We'll add a few more points and do the problems given in these textbooks. Thank you very much.